Hello and welcome to YMT211 Discrete Mathematics. Today we are taking our first tutorial session. We have already studied enough to cover it in tutorial. Today we will discuss few examples and I will explain whatever needed for you to solve the rest. I will also create an assignment for you based on what we explained in the class and what we are going to discuss within this session. Let's take these examples one by one and see what's requested and discuss the results or the answers. Let P and Q be the propositions, the election is decided and the votes have been counted respectively. So P is the election is decided, Q is the votes have been counted. Now what is requested? The requested here express each of these compound prepositions as an English sentence. Alright, in order for us to express these compound prepositions, we need to understand the meaning of the given preposition, whether it is compound or not. All these are compound because the least of them is composed of not P, for example, or not Q, or whatever. Look at the preposition, the election is decided. Let's take A, the election is decided. If we want to negate it, it means not the election is decided. We don't say that in English. In English we say the election is not decided. So this is A. Let's take B, P or Q. Alright, the election is decided or the votes have been counted. As easy as it is. Not P and Q, not P, we just created it. The election is not decided. Alright, and the votes have been counted. Right, Q implies P. Pay attention to which one implies the other. If Q, then P. Alright, in this case, if the votes have been counted, then the election is decided. Alright, let's take E. Not Q implies not P, and you guys are familiar with this, we explained about it. Okay, now not Q, the votes have not been counted. Not P, we said about it, the election is not decided. Not Q, if the votes have not been counted, then the election is not decided. Take the other way around. If the election, this is F, if the election is not decided, then the votes have not been counted. You can do the rest of them. It's really easy. Exactly. Let me do this. P, if and only if Q. Alright, how do we do it? P, if the election is decided, the election is decided because this is not if only. The election is decided if and only if the votes have been counted. That's it. You can do the rest, only one left. It's easy. Let's go to another type of questions and see what we usually request. We may use bitwise operations, and we ask these questions also in discrete mathematics and logic circuits. You need to get used to them. Evaluate each of these expressions. I put A and C there. This is from your textbook. There is also B and D. I just ignored them. We can change. I can change this one to B. It's all right. But what I'm saying is, if you understand one, you can apply to the rest. Now you need to understand the operation in between, or what creates the compound expression. Now look at these expressions. Now we have two parts. The first part is this one. The second part is this, and this one is divided also. Is composed of two parts with the conjunction and the disjunction. What we need to do, now remember that this one has higher order, higher precedence. Why? You remember whatever inside parentheses is done first, so we do this first. This is OR. When you OR each bit with its coincided bit from the other side, means what? Look at those. Now if you count 2, 4, 5, here 2, 4, 5. Let's say for some reason, if I give you less by 1, here, what will happen? I removed 1. You just embed a 0. Okay? you embed a 0. But it is available, so you don't do anything. So you AND a bit with a bit. 0, sorry, you OR. This is OR. 0 or 1, that's 1. 1 or 1, that's 1. 0 with or 0, that's 0. 1 or 1 is 1. 1 or 1 is 1. So this is the outcome here. Now, this one remains same. Why? Because we have to finalize this first. We have to achieve its outcome first. Now we apply the conjunction and ANDing operation. 1 and 1 is 1. Now, again, you count them 2, 4, 5, so the number of bits are similar. If not, embed zeros with the missing number or sequence of digits. 1 and 1 is 1. 1 and 1 is 1. 1 and 0 is 0 and 0 is 0. 0 and 1 is 1. Now I'm saying 0 and 0, the coincided bit. We move from the most significant to the least significant, or if you like, you go from least significant to most significant, which is not actually the convention. The convention, we move from here to here, usually. Okay. So 1 and 1, 1. 1 and 1, also 1. The rest, since we have zeros, do not waste your time. You can take a short circuit. Why? ANDing a 0 with anything is a 0 with ANDing 0 with, and the 0 and 0 is 0, 0 and 1 is 1. So when you have zeros, just immediately list them down. Let's take another operation, XOR. Now for XOR, also again apply the same concept, go a bit at a time, and what you need to do is you need to know the outcome of the XOR. Exclusive OR means what? Means we compare the bits. If they are equal, then the outcome is 0. If they are different, then the outcome is 1. Alright. Now, what we need to do, we start by the one encapsulated by these parentheses. 0 XOR 1, that's 1. 1 XOR 1 is 0. 0 XOR 0 is 0. 1 XOR 1 is 0. 0 XOR 1 is 0. So we have 0, 1, 0, 0, 0. Alright. Now, sorry, not this one, 1, 0. I got confused. 1, 0, 0, 0, 1. I said it was a bit different from what I achieved. Again, let's just finalize. 0 XOR 1, that's 1. 1 XOR 1 is 0. 0 XOR 0 is 0. 1 XOR 1 is 0. 0 XOR 1 is 1. So 1, 0, 0, 0, 1. Alright, XOR it with this again. 1 XOR 0 is 1. Okay, here. 0 XOR 1 is 1. 0 XOR 0 is 0. 0 XOR 0 is 0. 1 XOR 0 is 1. And that's the outcome. As easy as it is. There is no much of complication here. Let's take another type of example, common example. We usually ask quizzes, exams, and the solution is intuitive actually. If you want to apply a long process of answering it using truth table, you'll really take long time, spend your effort. The time of quiz or exam will finish maybe before you achieve anything. Why? Now, I'll explain why. Determine whether the following compound proposition is satisfiable. What does it mean satisfiable? We said that at least it has to have one true in its truth table after all. So it should yield at least one true in the outcome. So we need to look for a true from all this compound proposition based on whatever values we give to P, Q, R, S. So saying that we have P, Q, R, S, if I want to compose truth table 2 to 4, that's 16 combinations, that's really too much. Can I solve it by an easier way? That's what I said. If you want to go to truth table, it's likely that you get stuck somewhere, and that's not recommended. You need to save time usually while answering such sort of questions. And now let's just give it a shot with all zeros. P is 0, Q is 0, R is 0, S is 0. That's the first row in our truth table considerations or possibilities or combinations that we set. All right, now look, I have conjunction or ANDing, 4 or 5, 4 different AND operations Okay. What is between these and? We have OR operations. Good. In order for us to get 1 or true, all these and, here must be 1, here must be 1, 1, 1, 1. So we are looking for 1 here, 1 here, 1 here, 1 here, 1 here. This is the easiest way. Now look, all zeros, let's try. 0 or 0 is 0, or not 0 is 1. Because all zeros, that means R is 0, not R is 1. Okay, we guaranteed 1 here. Let's apply to the next. 0 or not 0 is 1. You don't have to carry on. Why? 1 is enough. Once you get 1 for OR, it's like a short circuit. You don't have to carry on here. Don't waste your time. Not Q means not 0, means 1. 0 or 1, that's enough. You got the second one. Let's see if we can get the third. P or not R, yes, again 0 or not 0, 1. You don't have to check this. Third one is guaranteed. Fourth, here for the fourth one, not 0. Okay, don't go ahead. That's 1 enough. Whatever you OR it with, 1 or 0, the outcome is 1. Let's check the last one. We have also negation here. So 0 or 0 is 0, or 1, not 0 of course is 1, or not false is true. That's 1. So we got 1 here, 1 here, 1 here, 1 here, 1 here. 5 ones, and it all together, that means we have 1. We have true. So that is at least 1 from the truth table. Guarantees that we get the condition of satisfiable. And this is a common question. We usually ask a lot of such similar questions. This one is also a common question, the number 4. Let P be the P of X, sorry, be the statement X spends more than 5 hours every week in class, where the domain of class consists of all students. I speak about all students. Let's say all students who are taking discrete mathematics, a YMT211, the one we are taking now. Express each of the quantifications in English. So we look at these quantifications, we need to express them in English. How do I express them in English? I need to understand the meaning of this. There exists a value of X such that Px is true. Okay? Or for that, Px is true. It's up to you, it doesn't matter, because you can express it in different ways. Right, what are the values of X? The values of X, all students. All right? And here, what's the predicate? X, or student, spends more than 5 hours every weekday in class. All right, so there exists, or there is a value of X. In this case, let's make it in a proper English sentence. There exists a student. And X here is a student who spends more than 5 hours every weekday in class. Okay? There exists. Then apply the predicate. A little bit of modification. Why? Well, we don't speak about X spends. We speak about there exists a student who spends. You need to use some proper connector here to make your sentence sound more logical, or the structure of the sentence itself will be more valid. I don't want to play the linguistic game. This is not an English class, but if you do it close to this structure, I would accept it. It should sound in the logic. At least this logic should be correct. If you put who, that, it doesn't matter to me, because I'm not going to mark your English. All right. Okay, let's go to the next, B. Now, we know that for all values of X, this one is the universal quantifier. This is the existential, this is the universal. So there exists X for all values of X. Px is true. Okay, what are the all values of X? All students. So in that case, we have to replace X spends by all students. All students spend more than 5 hours every weekday in class. And that will do. That will replace this. How about C? C is a bit different, but we know there exists a student, but here not. So we need to create the negative statement of this. Okay. there is a student spends more than 5 hours every day, at least a student. In this case, we need to negate this part. There exists, keep it the way it is because it's not negated here. A student who does not spend will be negated by who does not spend. Okay? Some students in the past, I got something like this, who's not spending. Well, I said I will not play the language game. It's not about the structure of the sentence. I would accept it, but try to do it this way. I would appreciate if you place it or compose it in the form that's given in the question. You want to negate the sentence does not spend. It's much easier, much more fit. It looks like you understood fully the course. All right. We apply the same to this universal quantifier where we have a negation of the statement itself. So we know that who does not, but remember here we speak about all students. So we say all students do not instead of does not here because we speak about plural. All students do not spend more than 5 hours every day in class. Well, seems extremely straightforward and there is no problem with it. Usually I ask such questions, not much different. I mean, the idea should be around the same. Of course, I put some of my own touch, but if you understand these fully, you'll not have a problem answering my questions. All right. And all these questions I have not created. I took from your textbook. I never created any of those. I didn't change any of them. I just used them from the textbook. You can go through the textbook. There are many others also. You should train yourself. I will give you also assignment from your textbook. You should try to solve them. All right. Let's go to another type. Suppose that the domain of propositional function, the propositional function given here, px, consists of -5, -3, -1, 1, 3, and 5. Some numbers, okay? Some integer numbers. This is the propositional function, or predicate if you like, if you place some conditions here. Right, express these statements without using quantifiers. Now we don't want to use quantifiers. Instead of quantifiers, instead, using only negations, disjunctions, and conjunctions. So we can use negation and or and. Okay, so that's how the way we're supposed to compose the statements. Now let's look at the first statement. There exists x such that px is true. Well, when we say there exists x, or there is a value of x that makes px true, at least one value. Well, here we don't have any condition. So what makes px true? All of them. Well, how do I know? Because there is no any limitation, any restriction. Px can be p of -5 or p of -3, p of -1, p of 1, p of 3, p of 5. Or y, existential, or all the elements in the domain create the predicate or the propositional function. And you remember this. We apply the disjunction for all possibilities or elements. How about the universal? For the universal, for all values of x, px is true. What are the values of px here? Do we have any restriction? There is no restriction. Again, but what we need to do is we don't apply the disjunction, rather we apply the conjunction. Why? There exists, could be any of them. But here, for all values, the conditions must apply to all of them. Instead of telling that p of -5 or, we say p of -5 and, for this one, and p of -3, p of -1, and p of p of 1, and p of 3, and p of 5. So you apply and between the elements, and you apply the conjunction between the elements. We explained about this in the previous class. This one has a bit of an idea for all values of x, except actually something here. When, if x is not equal to 1, then px is true. Well, for all values of x, we just did it, but we have an exception. What's this exception? The exception says exclude when x is 1. How do I know? X is not equal 1, when x doesn't equal 1 or is not equal to 1, then px is true. If then. So we have an exception. You take out when x equals 1, then and all the rest means what? It's same like this one. We have only exception when x is equal to 1. Right. P of minus 5 and P of minus 3 and P of minus 1. This one is excluded. P of and P of 3 and P of 5. Why 1 is excluded? It's written to me here. Other than x equals 1. Alright, let's take the one next. For all there exists value x such that x should be greater than or equal 0, and at the same time it applies to px. That means in px, or px should be true only and only if x is greater than or equal 1. Why do I say only and only? Because we have and here, and applies in the case that this one is valid. There is no other way. Here we don't have restriction because it's given, all the domain is given to us. This is the restriction. When x is greater than or equal 0, what's greater than or equal 0? It's positive numbers, these here, given here. Means p of 1 and p of 3 and p of 5, and that's it. Sorry, not and here, or. I thought it was universal. This is existential oring. So we say again, sorry about that confusion, p of 1 or p of 3 or p of 5, because this is existential. Any of them, any. What we did here, we apply, but only when x is positive. Well, how about E? E is has a bit of an idea. I'm not going to answer it, but I will give you the clue, the trick, how you will answer it. Now look, you have a composition of two propositional statements or compound statements here. You have the existential quantifier of a negated px. How do I get this one? Put not p of minus 5, not p of minus 3, not p of minus 1, so on. Alright, so that's all what you need to do. And you need to OR all of them. So ORing all of them means what? Look at this. The answers here we got. No, I'm sorry, I went far. Yeah, here. Those, p of minus 5 or it will be not p of minus 5 or not p of minus 3 or not p of minus 1 and so on. There would be no much of a change since the negation is applied only to the propositional function. Alright, how about this part? Well, we are familiar with this part. We did something similar here or here. For all values of x, when x is less than 0, or negative ones here, minus 5, minus 3, minus 1. What do we need to apply for all values? That means ANDing. This applies, or this makes px true. And in this case, what we need to do, px will be true only and only, not only and only, if x is less than 0, or px, p of minus 5, p of minus 3, p of minus 0. And remember that this is universal, so we will take their ANDing. The first part, ORing, all of them, but negated. So what are all of them? P of minus 5, it will be not p of minus 5, not p of minus 3, so on, not for all of them. This part will be when x is less than 5, less than 0, ANDing p of minus 5 and p of minus 3 and p of minus 0. So you got it. Here you have, again, and between these two, apply it, and that's it. You got the answer, you got the outcome. Well, this is it for this question. It's not really hard. Just try to do this one. It's not that much difficult for you to do. I decomposed it for you. Let's talk about the proof. Let's take just one simple example. Prove that m squared equals to n squared if and only if, now pay attention to this because it matters while proving, m equals to n or m equals minus n. So we have, or here we have two or compound possibilities by or, and here we have if and only if. When we have if and only if, we have two parts of proof. We need to prove that m squared equals n squared when this one is true, the other part is true. This one means what? We need to assume that this one is true and prove this one is true if we take direct proof. If we don't take direct proof, or whatever proof we follow, we need to prove that this one is valid, true, and this one the other way around, m equals n or m equals minus n, when it is true, this one is also true. It's like two-sided or biconditional. If then, we need to prove both of them, both sides. Alright, in order for us to prove, we can use direct proof. It sounds applicable, let's try to do it. In direct proof, you assume that this one is true, and then you prove that this one is true. So true implies true is true. Okay? Assuming that this one is true, m squared equals n squared, then what we need to do is, well, you can decompose this or manipulate it, defactorize it. We can get the factors of this one, factorize it by which way you like. Now, if you drag n squared to the left-hand side, it would be m squared minus n squared equals 0. You can create or whatever, use whatever method you like to factorize it and get the answers. What we can use here, m plus n, parentheses multiplied by m minus n. There are different factorization ways. This is extremely simple, and this we are not going through them. This is not exactly course for classical mathematics. We study discrete mathematics, but it's just good for you to revise these things, why they help you solving our own discrete mathematical problems. Okay, so when we factorize it, what we can get, or what are the possibilities, either m equals minus n or m equals n. These are the two possibilities here based on the factors, and this is exactly what we are looking for. Assuming that this one is true takes us back to this one. Either m is equal n or m equals minus n. It doesn't matter, the order here doesn't matter, as long as it is applicable to these two. Let's take the other way around. If we assume that m is equal to n or m is equal to minus n is true, okay, we assume that this one is true, that implies m squared equals to n squared is also true. So we need to prove that this one is true based on this assumption. True implies true, takes a whole statement to a true state, and that's what we are going to do. Assume that m is equal to n, substitute, well, n squared, is it equal to n squared? Yes, that's it. Substitute in the equation, just substitute. M equals n, substitute, n squared is equal to n squared. Again, because we have or, m equals n, minus n, sorry, substitute, minus n, parentheses, all inside parentheses, like here, all squared, is it equal to n squared? Yes, sure, and that's the proof of the second part. So now remember, if you get any statement or conditional statement or something that you are supposed to prove with if and only if, you need to do the first part. That means if then for the first part, from left to right, then you will need to take from right to left. If then also from right to left. The other way around as we did here. This is the end of this session. I'm trying to keep it as simple as it is. I will create another session soon enough. Until then, have a good time. Goodbye.